Hello, my name is Keith Dunnavant, Manager of Data Center Cooling Solutions for Munters, North America. In this video segment, I'll be discussing indirect AirSide economizers. This is the first part of a three-part series on this topic. Before I get into an indirect AirSide economizer discussion, though, it's beneficial to discuss a direct AirSide economizer so that you can appreciate the differences. With a direct AirSide economizer, you're cooling the data center using outdoor air. And so I'm going to walk you through how this works. You've got outside air coming in through first a louver, a filter. It then flows through a supply fan, and after going through potentially cooling elements, and delivers that air into a cold plenum. Picks up the heat from the servers, goes into a hot plenum. Now, some of that air needs to be exhausted because if you're cooling with outside air, you're adding pressure to the building. That pressure has to be relieved, so you have exhaust fans with variable speed drives normally to maintain the building pressure. Then you've got, during colder winter conditions or cooler conditions, you've got recirculation air coming back as well. So generally, if the outdoor air temperature is below your desired target supply temperature, then you're going to need to recirculate some of that warm air back to blend with the cooler outside air to achieve the proper temperature. And so you do that by mixing dampers. You're varying the amount of outside air and recirculation air in that mixing plenum before you're then delivering it back to the space. So that's a direct AirSide economizer, and a common element that's used in direct AirSide economizers is direct evaporative cooling. A direct evaporative cooler provides two benefits. One, it cools hot, dry air, and it can also allow for winter humidification. So you've got air flowing through this media, and if you look at it on a cyc chart down here, you'll see that it's a constant wet bulb process. That air flows up through the wetted media, picks up moisture, and is cooled down. Munters is a global leader in the manufacture and sale of evaporative cooling media from glass deck, cell deck, and other types of media that you can read about on our website. Here we have a perimeter mounted direct evaporative cooler. There's no refrigeration installed. So this is a direct AirSide economizer suitable for dry desert climates for cooling data centers. So I'll walk you through this. You've got your warm air coming back into a return header. Some of that air enters the system and may be exhausted during the winter months. Some during the winter months is recirculated, and we often have a 1/3, 2/3 damper segment, so that during the cooler periods we operate the upper segment of dampers to promote better mixing with this warm air before it then enters the supply fan and can go through segmented evaporative media stages. 4-inch and 8-inch media in series is common, with a modulating bypass damper. So the combination of staging and modulating your bypass allows for good temperature and humidification control before that air is then delivered back into a supply header and back into your data hall. You'll notice that we're only filtering the outdoor air to a MERV 13 level. Usually we'll put MERV 8 filters in the hood so that the outdoor air is first pre-filtered, and then it has a post-filter to the MERV 13 level. By only filtering the outside air, we're not adding any additional pressure penalty to the recirculation component, which helps save some energy. Here we're showing the operation of the direct evaporative cooler at an extreme ambient condition in Reno, Nevada. Their extreme wet bulb is 70 Fahrenheit. That occurs at a mean coincidental dry bulb of about 95. So I've plotted that on the psychrometric chart, and if you ride that wet bulb up, you can cool to 80 degrees, and it's just over 60% relative humidity. But it is higher than the recommended dew point. This has cooled to about 66, but you'll see that I've also plotted the TMY3 weather data, hour by hour, plotted in bins for Reno. So you'll see that this extreme is well outside of what you'll typically see. So normally on a hot day, you'll be at a much, much lower dew point. You can then ride that wet bulb and maintain a 75-degree temperature, so you can get even cooler and stay below the recommended dew point and recommended relative humidity range. So for climates like Reno, Prineville, Oregon, many other areas of the western United States and around the world in dry climates, the direct airside economizer with a direct evaporative cooler is a very good solution. However, as we move into the more humid climates, now I'm showing you the Washington Dulles conditions, also plotted on a psychrometric chart. And in Washington Dulles, you'll see that there's 27.5% of annual hours where the ambient dew point, which is a measure of how much moisture there is in the outside air, has exceeded 59, which is the upper end of what ASHRAE recommends for a supply air dew point to be supplied to a server. So for all these hours, almost 30%, you would have to disable a direct airside economizer. It's too humid to introduce that air into your data hall, so you'd have to revert to 100% recirculation and utilize some either chilled water DX or perhaps water side economizer cooling to reject that heat. Summary of direct airside cooling systems. Number one, it is efficient cooling during cool and dry conditions, but it can be very inefficient during those humid conditions when you go to full recirculation air cooling with full refrigeration potentially. Because you're cooling with outdoor air, you're bringing those outdoor air pollutants into the space, which introduces a risk for potential corrosion on the circuit boards. Next, you've got high filtration costs. You're introducing all of that particulate from the outdoor air. That's little by little plugging up those filters, and those filters have to be changed out as the pressure drop increases. You've also got modulating outside air and return air, dampers, relief fans with drives for pressure control. Overall, it gets a little complicated to control these systems. When you're in winter humidification mode, there can be risks of freezing water on the evaporative media, so that's another concern. Also, because you're introducing outside air for cooling, which has various moisture levels in it. In the winter, it's very dry. In the summer, the moisture levels is increasing. So you're impacting the space humidity levels, and you're also impacting the pressure of the room, which has to be controlled by that relief fan. The rapid restart is there for these types of systems. On a loss of power, they can restart very rapidly. We're bringing the cooling back online during all of those economization hours. However, when you are in recirculation, refrigeration-based cooling, you're subject to whatever delays the DX might have included for a rapid restart. Partial PUEs of these types of systems can be the lowest of any method of cooling a data center. If you optimally design a data center in a dry desert climate, sizing your filters very large for low pressure drop, eliminating your ductwork using supply plenums and return plenums, keeping that supply fan power level down low and your exhaust power levels down low using efficient motors and everything, it is absolutely possible to achieve partial PUEs as low as 1.01, which is the most efficient way that I know of to cool a data center. Now we're going to compare that direct system to the indirect airside economizer. And so now we're cooling with outdoor air indirectly. We are not going to be introducing outside air directly into the data center. We're going to use outside air to extract heat through an intermediary heat exchanger. So here we have the air supplied to the cold plenum, again picking up heat, recirculating it back into a return fan, and then through a heat exchanger before it is then cooled back down as needed to be delivered to the space. Outdoor air is introduced through a washable low pressure drop filter, through an optional evaporative cooler, then through the heat exchanger, extracting the heat from the recirculated air into a fan, and then that heat is exhausted out the back. So this scavenger fan, we call it, has a variable speed drive on it. It speeds up if it needs to extract more heat. It slows down on the colder days when it needs less heat extraction to get the supply temperature to the proper air temperature. There are 3 indirect cooling methods. In each of these, heat from a recirculating airstream is rejected to ambient by means of a heat exchanger. The first type is an indirect AirSide economizer with a dry air-to-air heat exchanger, such as a heat wheel, a heat pipe, or a plate-type heat exchanger. This may have a scavenger air evaporative pre-cooler included with it. Secondly, you have an indirect AirSide economizer with an air-to-air heat exchanger that operates wet during the warm periods for indirect evaporative cooling. And thirdly, there's an indirect AirSide economizer cycle that uses a cooling tower or a fluid cooler piped to a cooling coil that's contained in the air handler. I'm going to be discussing options 1 and 2. I'm not going to be talking about option 3. Looking at your different heat exchanger types, first we've got a plate type heat exchanger, typically operates in the range of 60 to 70% effectiveness. Next we have a heat wheel type heat exchanger, operates usually 65 to 75% effective. And then lastly, a heat pipe type heat exchanger, operates 60 to 65%. Munters makes all 3 of these types of heat exchangers and many more. This is a counterflow aluminum plate type heat exchanger. It's been coated with epoxy, and this is a very good way to a very good heat exchanger choice for an indirect AirSide economizer. No moving parts, very low maintenance. Heat wheels is next, and Munters makes heat wheels up to 14 feet in diameter. This is a heat wheel in the Munters factory, and with this type of heat exchanger, we're going to bring hot data center air through 1/2 of the heat wheel. We're going to bring outdoor air in through the other half of the heat wheel, and as this heat exchanger rotates, the cool air flowing through the upper half is removing the heat and rejecting that to ambient, and having then cooled that matrix back down as it spins back over, it can absorb that heat again from the warm data center air that's being recirculated through the lower half. Here's a Munters manufactured indirect AirSide economizer that uses a heat wheel. This is one of several installed in Quincy, Washington on a 10 megawatt data center. The heat wheel is located inside the box about here, and we're going to bring return air back. It's coming up through the roof into the unit at about 95 degrees. It flows through the heat wheel, the lower half, where it's cooled, and then delivers that air back to the data hall at 75 degrees. Outdoor air is introduced in the upper half, and if your outside air is about 64 degrees or cooler, you can extract 100% of the heat with the heat wheel. No supplemental refrigeration is required, which is most of your operating hours in climates like Quincy. This is a schematic showing the inner components of that system. This system is rejecting 450 kilowatts of heat from that data center. It's got 75,000 CFM of recirculating air flowing through the lower heat wheel segment. It has 160 tons of onboard DX. With 95-degree return, when this outdoor air is 95, there is zero benefit. There's no evaporative assist in this system, so the heat wheel stops rotating and that air flows through, and now we have 100% DX cooling that must be applied to reject that heat. So 160 tons of DX. Here's your condenser coils and compressor set. Now you've got hot air being exhausted out onto the roof of the data center. Again, this particular unit had a 14-foot diameter heat wheel. Next, we have heat pipes. Munters makes these of various diameters, 1 inch or 1.5 inch diameter. They are extruded aluminum construction. They can be coated with various corrosion inhibitors. They have a tight seal between the two separate air streams. And the way heat pipes are made, they're connected up to a vacuum pump. You can perhaps see this. There is a Schrader type fitting on the one end of the heat pipe. It is evacuated and then charged with refrigerant. So there's nothing in these tubes except liquid and vapor refrigerant. And now, once it's sealed up, it's ready to start transferring heat. So a good way to install a heat pipe in a data center cooling unit is in a vertical orientation. So here's a vertical heat pipe installed inside a rooftop indirect AirSide economizer. So we have our return air coming into the plenum type supply fan through the filter, through the lower half of the heat pipe. This is showing supplemental DX cooling before then delivering that air back to the data hall. And again, we're using outside air, MERV 8 type filtration, pushing that air through the heat pipe to extract the heat. And if we need to use DX, we have our compressors and condensers up here to do full DX cooling with this type approach. Overview of dry heat exchanger designs. Number one, they require full DX on hot days, and thus there's no benefit of downsizing of generators, switchgear, or the connected electrical wiring. There's no reduction in peak electrical demand. On the hot day, the heat exchanger provides no benefit, so you can't shunt any electrical demand. Heat wheels and heat pipe designs require MERV 8 minimum filtration on the scavenger air, requiring frequent replacement. Heat wheel designs leak air from the scavenger to the process or vice versa, which can result in the introduction of excess ventilation air that impacts both room pressure and humidity. And lastly, heat wheels require maintenance. They have seals that must be adjusted, belts that must be tensioned, etc., unlike the plate types and the heat pipes, which are completely passive and require no periodic maintenance. Here we have a annualized performance for various U.S. cities in terms of ton hours of contribution from both the heat exchanger and the refrigeration component. For this example, we're looking at 95-degree return, cooling to 75 degrees Fahrenheit supply, and using a 65% effective air-to-air heat exchanger. In Ashburn, Virginia, this is going to operate for almost 90% of the annual ton hours we're going to be able to reject with just the heat exchanger. 11.3% of the annual ton hours are rejected with DX, and that's pretty good. In Portland, almost 95% of the annual ton hours can be rejected with the heat exchanger. A little over 5% is rejected using the DX component. Now, when you're rejecting heat with the heat exchanger, you are doing that at about a 0.25 kW per ton or lower in terms of a efficiency metric. So that's a coefficient of performance of 14 or higher. So when you can reject heat with a air-to-air heat exchanger, your only consumables are the supply fan to push that air through the one side of the heat exchanger, and the scavenger fan power to push it through the opposite side of the heat exchanger, and potentially the scavenger filters. If you add all of that up, and if you're operating with heat exchangers that have no more than about 1 inch of water column peak pressure drop, you're going to achieve that heat rejection at 0.25 kW per ton or lower. So pretty efficient compared to most refrigeration systems, which are at best about 0.75 to 0.8 kW per ton on mild conditions and over 1 kW per ton on hot days. This is a patent filed by Dr. Nick Deschamps back in November of 2001. And I'm showing this just so that you can see Munters is a pioneer of the indirect airside economizer concept. These strategies have been used at Munters Deschamps for many years, and used very effectively to reject heat from a number of closed loop processes such as electronic cooling. That concludes this video segment. This is the part one of a 3-part series, and you can look for more details on the Munters website. Thank you.